Yesterday we talked about rolling motion, and we used energy to make progress, but often we need to look at the dynamical picture. So we started to talk about rotational dynamics with an aim towards rolling motion. And I commented to you that what we established last chapter, we derived this for a fixed axis. It's also true when an axis moves parallel to itself, like in rolling, in case we're interested in rolling motion. It also happens to be true about the instantaneous axis of rotation. And I'll remind you what that is today. We're going to do the demonstration that involves that today, and I'll remind you. So as an example, we solved this problem right here. We have a rolling body. We're not specifying the moment of inertia. That's fine. That makes it more general. And it has, you can imagine, it has some kind of fixed axle here, an axle fixed to the body. And somebody's exerting a force on this, and I just remembered that I did an experiment on this with an undergraduate. So here's what we were interested in. Raising a disc over a step. So we had this body here, and we had an axle attached to it, and we had a step here. Okay, we're in a gravitational field, and we did a theory and experiment on two cases. One case where you exert a force here, and we exerted the force with a hanging weight. Okay. And we knew what the force was because this is all essentially static. So in this case, we know that the tension in the string is going to be the hanging weight, right? Once it starts accelerating, it's no longer true, right? The only way this can accelerate downward is the force of gravity has to be bigger than the tension, so you got to solve for the tension. But this was essentially a static experiment. And can you guess what the interesting thing in here is? What we were after? What does it take to get it to go over the step? And that's an instability. Once it starts to go over, it's gone. So we also did this case where we exerted a force here, again with a hanging weight. And yeah, so, and you never know what's going to happen when you do that. We're comparing it to theory. We had actually a lot of trouble. We had to make sure, we had to reduce the friction in the pulley here and make it very light. And we vibrated the table to break static friction. And we found that we didn't get very good results at first. The results are very sensitive to the nature of the step here. We had deburred the step here, you know, filed it down very lightly, or right, so that to take the edge off of it. That made a difference, a noticeable difference. You never know what you're going to find in an experiment.
Did you try different radius of the circle or hoop, whatever it was?
This was this right here was a fixed body. Yeah, which is all that's really important here. I don't think the moment of inertia is important here. And it was not a regular disk. Yeah, the moment, it's just the center of mass is at the center. That's all that's important. The moment, this is a static situation. The moment of inertia was irrelevant. So we published the results. And the undergraduate went on to get a PhD in physics. She's a physics professor now. Okay. Sorry, I just hadn't thought about that in a long time. If you want to see the paper, you know, I have a PDF of it. Send me an email message. All right, so we did this problem here, right, with no step here. And now we want to do a second one. Second problem here. Here is, I had to make this big so you could see all the, we're going to write all the vectors here. This is a body rolling down an incline. So now, instead of this previous case where we had it was level and we were exerting a force, now We're going to look at this problem. So let's look at the, we're going to call this the x-axis. It's going to accelerate down the ramp. We'll assume it's released from rest, although it's not important here. Y will be perpendicular, and the forces in the x direction are, there's a component of gravity, force acting in this direction, mg sine theta, where this is theta, the angle of inclination. There's going to be a static frictional force. We'll assume this is rolling without sliding, so it's a static frictional force pointing in the opposite direction here from gravity. And that must be, by Newton's second law for a system of particles, which is very general, the net force on the system. And the internal forces cancel in pairs here. So the net force is necessarily the net external force. It's equal to the total mass times the acceleration of the center of mass, which is not obvious. Remember, we talked about that in the past. But it's very easy to remember. It's F equals ma. You just got to make sure you understand that a is the acceleration of the center of mass. In the y direction, we're not going to really get anything out of this, I don't think. Because there's no acceleration of the center of mass in the y direction, the normal force has to balance mg cosine theta, right? And then we can't solve this system. We have to have another equation here, and we get it. It's the rotational equation. We look about the center of mass, and you can see that the net torque here, there's no torque due to gravity about the center of mass. The moment arm is 0, okay, or for the components here. So there's one torque, and it's due to the static frictional force. And the torque is the force. It's perpendicular to the radial arm here. It's the force times the distance r. That's the torque. And that's going to be the moment of inertia times the angular acceleration. Because there's no slipping, alpha is equal to ACM over r. It comes from V is equal to omega r, as we've seen many times before. So it's going from here to here that we input the information that it's not slipping. Now, if you look at these equations and compare them to the last problem, they're essentially the same. Okay? This is essentially the same problem. The only difference is we now identify F. It's mg times the sine of theta. So we can use that result. We don't have to resolve this. The solution is going to be just like the previous one, where we simply replace F with mg sine theta, which is physically very reasonable. And you can look at the math and see that it's essentially the same problem. So we can just take the result, replace F with mg sine theta, and this is the acceleration of the center of mass. This is not a good form for the expression. It's much better to divide by m. And now we have this expression. This is nice because if the object slides without friction, we know that's going to be the acceleration, right? So this is how it gets modified due to the fact that there's rotational inertia and it's not slipping. And it involves this dimensionless number here, the moment of inertia about the center of mass divided by the total mass times r squared. So now we can go down as the same path we did with the energy approach, except now it's more direct. Now we've actually found the acceleration down the center mass. We actually inferred that by the energy approach, right? If it's putting less energy, as the object's rolling, it's putting less energy into rotational kinetic energy, it has to be accelerating. But that was really, it's indirect. I mean, it's not that indirect, okay? But here we've explicitly found the acceleration. We found it here. There's the formula for it. And now we can make a table. So this is very similar to the table before, except now we actually have explicitly the acceleration of the center of mass. And I'm going to add right here is the spherical shell. I'll add that. And so now we see, just as same thing that we concluded before, although it was a little bit indirect, we've shown here that that the greatest acceleration is when you have no rotational kinetic energy, an object sliding. We can get that from our answer by setting the moment of inertia about the center of mass equal to 0. And that has the greatest acceleration. And then the solid sphere, that's next in the order of how the mass is being, if you imagine the mass being at the center, for this case, 0 moment of inertia. Next up is going to be the solid sphere has this acceleration, and then the disk, and then the worst is the hoop of these examples here. Okay, any questions about that? Okay, so let's do some demonstrations here. So there's a yo-yo. Okay, and we're going to actually do an example, do a quantitative example of this. So here's our model for the yo-yo. We have this string wrapped around this axle that's fixed relative to the, well, let's not worry about this sleeping, right? How that's handled. Oh, do you guys know what that means, sleeping for a yo-yo? Okay. Yeah, yo-yos are just never going to die, are they? I guess it doesn't matter how high-tech we get. I think they'll still be, yo-yos will still be around. So here we have it. We're going to imagine releasing this from rest, and it's going to fall down. And there, that's the sleeping, right? So it accelerates down, and you'll notice here that it doesn't accelerate very fast compared to G. It's not, the acceleration is substantially less than the acceleration due to gravity. So we can actually quantify that. So here's the force-torque diagram. From here, we write down Newton's, I think I told you guys in the beginning of the course that we're always going to take up to be positive. Boy, that was a lie. Okay, here we go, but I think you're used to it by now. It's just natural to choose down as the positive direction here. So you can see I'm choosing that to be the positive direction. And the tension is fighting that, whatever that tension is. But I can tell you it's not mg. I can tell you that it's less than mg, right? It's only mg if you froze the string here. If you somehow didn't allow, just looked at this statically, it would be mg. It's going to be less than mg. So we have two unknowns here: acceleration, center of mass, and the tension. Now for the rotational motion, we'll look about the center of mass here. There's a torque. Gravity exerts no torque about the center of mass. The torque is just going to, again, it's simple here. It's the force times the distance. This moment arm distance here, which is just the radius. It's little r, not big R, right? That's important. It's the center of mass. We'll assume, we're just going to take it because we want to get quantitative results. We'll assume it's a uniform disk. That's an approximation. It's just a simple model here. And that's going to be, right, the torque is the moment of inertia about the center mass times the angular acceleration. Because we're assuming no slipping here while it's accelerating down. The slipping just occurs at the bottom. Or maybe near the bottom, I don't know. Yeah, I think it's right at the bottom. Anyway, we again, like I just mentioned, we replace alpha with ACM over R. Okay, now we have two equations and two unknowns. We don't know the tension, we don't know the acceleration of the center of mass. So we can eliminate the tension. The easiest thing to do here is just divide by this little r, divide this side and this side by little r, so we get little r squared down here, and then add the left sides and add the right sides. We've talked about this before, and you cancel the t. But however you want to do it, doesn't matter, it's elementary. And we get our acceleration. And now the interesting thing here is to roughly estimate this. And I realized this morning I'm going to have to go in here and measure what this typical, what's important is the ratio. We can see that what's important here is the ratio of the radii. It's just the ratio of the radii that's important. And I need to go there and measure what this typically is. I'm going to say, and it looks roughly right. I may be overestimating or underestimating the ratio, but I'm going to take it to be little r over big R to be 1/10. I think it's probably a little bit greater than that, but that's roughly right. Okay, 1/10. Is that okay with you guys?
Yeah.
Okay, good. So look at this. This is interesting. See, and this is one of the reasons we do things quantitatively. All the physical, qualitative arguments in the world, you're never really going to be sure or that things are right or that you understand completely what's going on. You need physical reasoning and you need this quantitative stuff. And in fact, quantitatively, you need theory and you need experiments, right? So that's what we aim for and strive for in physics, is a physical appreciation, you know, experiments and theory, analytical theory. And there's another thing that people do that we can't live without now. What's that? No, in regard to what I just said about physics, is computer simulations, right? So I don't know if anybody knows what to call those. It's, in some sense it's theoretical, but in the other sense it's experimental. I think of them as like experiments, just very clean experiments, okay? But of course, you're putting a model system in there. So the connection with reality, you have to be careful about that. So that's another thing that we do. It's become just very standard. And I'm gearing up to do that for solitons on suspension bridges. So I'm not calling it Tectomanero's bridge anymore because I think people thought I was crazy, are thinking that I'm crazy, you know? So now I'm calling it solitons on suspension bridges. That sounds better, right? Yeah, so I'm trying to get a student to work on this, right? But it's so important that I'm gonna start next quarter. And it's down to, I've got to do computer simulations. There's no question. The analytical theory, I just don't think can be done. So it's computer simulation time. And they're simple computer simulations. Any of you can do it, computer simulations. With my help. Yeah, they're simple. It's a very simple model system. Okay, where were we? So the interesting thing here, look at this, the square, right? So if you plug this in here, you can forget the 1. That's not really important here because this is like 100 or 50, right? So we get that the acceleration of the center of mass is reduced from g, of course. It has to be less than g because there's this tension force. There's this tension force here. But the acceleration is remarkably small. And you saw it was small here. But that's interesting when you do this quantitatively. Why is it so small? How do we appreciate that? Look at the diagram here, the picture. Why is it so small? Well, what happens is what's going to happen if I keep reducing little r? Eventually, as little r goes, in the limit, as little r goes to 0, what's going to happen? It's just going to sit there. The acceleration is 0. So that's what we're seeing here. But what's interesting, I think, is the fact that it enters as the square here, this ratio. So you don't have to be that small to get a drastically reduced acceleration relative to gravity, acceleration due to gravity. Okay, now any questions so far? Okay, there's more here. So it's a real system, right? So there's actually two things here. One of them is this. This string is pretty thick, and I think you can see through this yo-yo. I got this, I don't know if you can see this, but you can see the string is being applied at a distance twice the axle, the radius of the axle here. Because why? In the beginning, why?
Wrapped around it.
Yeah, the string is thick. It's wrapping. So is the acceleration constant as this goes down? Nope, because the torque is going to be changing. The torque is going to be decreasing in time. So the angular acceleration will be decreasing. Now that's hard to see when you see this, do this. I think it's hard to see, right? So how do we observe it? Well, this is physics. We think, right? We think a little bit. So here's an identical yo-yo. Okay, they're different colors, but they're both fireballs. Yo-mega. It's kind of like yo-mama. What? Okay, okay, what? I'm missing all this. What? Is there anything I need to know what you guys were saying? Okay. All right. So, okay, now look at this. What have I done here? Did this last year for the first time. This is thin thread, much thinner than this string. So now I'm going to release them from rest at the same time. And what's going to happen? What do you think is going to happen? Remember, the green one has the string, as you can see here. Which one's going to, they're going to fall at the same acceleration?
Yeah.
Which one's going to fall at half a greater acceleration?
Green.
The blue, I hear blue and green.
Green.
No question. No question. Why did the blue one have,
There's a smaller radius.
yeah, it's a smaller radius, less torque. Exactly. Because the thread is much thinner. Okay, I'll just take care of that later. Okay, any questions? There's more. There's more about yo-yos. Does this bother anybody? Look at what we assumed here, that this was vertical and that this is going to just fall, and these remain parallel, these two forces here. Isn't this string gonna, isn't the center of mass gonna come over, and isn't the string gonna go like this? Isn't the center of mass gonna be underneath the support? If you attach the string here, so that if you attach the string, which means it'll be up here. If you attach the string here and you release this, what's it gonna do? It's going to oscillate. It's going to want to go back directly underneath, right? There'll be a torque, and it'll then pick up inertia, you know, and then go through, and it'll oscillate back and forth. But that doesn't happen here. In this case, which is good to look at this diagram here, we've started it out like this. It's going to stay like this. The center of mass cannot move horizontally because there's no force. There's no horizontal force in the system. So it took me only about 20 years to appreciate this. You think I'm joking. Maybe you don't think I'm joking. So, oh, see this beautiful chrome disc with holes in it? You know where this came from?
Germany?
Actually, it didn't. Actually, it didn't. Okay, but that's funny. You guys are funny. You remember one of the first demonstrations we did with the two identical looking hoops with the masses that you could adjust, and on one I put the masses out here and one like this, and I told you that the people who designed this, the masses were not, they were small compared to the hoop mass. This is heavy. This is steel. Okay, and so I replaced them with the plastic hoops. Yeah, so these are the original hoops, and they've got these nice holes in them to attach that bar. So I attached a string so that we could do this great demo here. I'm going to release it from rest. Now you watch carefully here. I'm going to release this vertically. Watch what happens. 1, 2, 3. Oh, wow, that was... It stayed vertical, right?
Yeah.
It stayed vertical. Let's see. Let's do this.
You got up on the table and released it from up there.
Well, yeah, I would use the ladder. Okay, I don't jump up on tables anymore. When you get old, you don't do that kind of stuff because you can end up in the hospital. And once you get in the hospital, there's a good chance you're going to die. You want to stay out of hospitals, okay? Well, you guys laugh, but you wait. When you get older, you'll be thinking about this kind of stuff. So, you know, old people injure themselves because they lapse. They think they'll just be. You could be walking along, and all of a sudden you feel young again, and you do something. like, you know, jump over something or, you know, and you learn not to do that because it can cause all kinds of trouble. So what I'm going to do now is release it like this. So the center of mass is directly underneath the support. You think it's going to go like this? No, actually we can use Newton's laws here, okay? That's sort of the basic idea of this course. There's a force that has a component this way, so this is going to move this way. And it should actually, we would expect it to oscillate back and forth, like I mentioned before, but watch what happens. The oscillations, I think, damp out pretty quickly, and it goes back to this situation like this, you know, where it's vertical. It goes back to this situation. Yeah, great demo. Nice hoop. Okay, now the classic one I mentioned. I think I mentioned this yesterday. I don't know, it was so long ago I can't remember, but it's this classic one, not that classic one. So this is a kind of a cheap spool for probably wire, I guess, right? So we've wrapped some string. We have a giant version. These spools can get to be huge, very thick wood for very thick cable. So years ago, like 15 years, roughly the early 2000s, there was some work being done on campus where they were using these big, huge cables for wiring or something, underground wiring. So there's a spool that has a 3-foot diameter, I think it's 3 feet, or maybe 4. I can't remember, 3 or 4 foot diameter disc, you know, on either side with this, it's all wood and with this wooden cylinder here. So sometimes people use those as tables. I've seen people actually use those as tables. It's not really comfortable or convenient, but you know, free, it's usually free or very cheap, right? So I grabbed one and we made a giant version of this with a big thick rope. And that, I'll tell you why it's important if I remember in a few minutes, but let me show you this one. So I'm going to do some demonstrations. First, let me do it. What's going to happen if I pull on the cord? It goes this way, right? Okay, that's the first situation there. What happens if I pull this way? Same way, right? What about number 3, if I pull this way? That's surprising. Most people, especially kids, find that surprising. So we bring this big one out when we're doing a demo show for kids. They're about, I think it must be 4 feet in diameter. And I have a still a picture of this the last time we did it. It's been a number of years. But this little kid, you know, got this rope and was real happy and pulled on it. And all of a sudden, this huge wooden thing was barreling at the kid. Just, and I hope it didn't psychologically damage the child. Yeah, I could get sued, right? For that. That happens a lot these days, right? So anyway. Well, what's going on there? Well, you can solve this. It takes effort. You can write down, you know, do the Newtonian approach, and you can solve for the acceleration. But we just want to get a physical feel for, we can solve it quantitatively. We'd like to get a physical feel for why you might think that when I pull on this, like I said, that it would go this way. And one very quick way to look at it is, that I didn't mention here, is that I'm exerting, well, there's 2 forces on this, right? There's the force due to the tension in the string, and then there's the static frictional force. So I guess it is conceivable that to get it to move that way, the static frictional force is going to have to beat out this force, just for Newton's second law for the translation of the center of mass, right? So that doesn't seem right, but there's a better way we can look at it here. And that's with the instantaneous axis of rotation. So we want to look at this over a small amount of time. where this is a different, very small amount of time, and the limit is that time interval goes to 0. Let's look at this situation right here. Here's my instantaneous axis. I'm exerting a torque this way. So the torque is actually, if you want to be precise about this, the torque is into the board, R cross F. The torque is into the board. What's the torque due to static friction? Please. Thank you. Because there's no moment arm, right? Oh, that's interesting. Yeah. When you choose this to be your axis, you've got now 2 torques. Yeah, this is a simpler way of looking at this. So we've got a torque into the board. The angular acceleration has to be into the board, so it's got to roll this way. Angular acceleration going this way is into the board. So that explains this. It also explains this. Okay. Oh. Okay, so I need to edit this. Yeah, thank you. So I can't believe this, that it did this. So what I'm going to do is take this arrow and put it over here. Right? This should be over here, just to compare it with that. So you can, the same thing's going to happen there. It's essentially the same as this argument right here. And what about here? Well, this same argument works. Surprising. It doesn't matter. You know, there's no torque due to the static frictional force. There's a radial arm or this moment arm, this R vector here. The torque R cross F is still into the board. It's the same argument here. It's just less. It's going to be less torque. So it tells you that it's going to have to go that way. And there's a way to test this theory. There's a way you can kind of test it. What if we apply the force at a certain angle here such that it lies along the line that goes through the instantaneous axis, instantaneous rest axis? I guess that's what I should, what do I call this? Instantaneous axis of rotation. Yeah, okay. What's going to happen here? What's the torque? Anybody? It's undeniable. I know you're not saying it because maybe you don't believe it or something.
There's no torque.
Exactly. It's 0. So what's the angular acceleration going to be?
0.
That's right. So let's do it. So I'm deciding this very roughly so that it's going through there. So as I apply the force here, okay, there. As I apply the force, applying force. Nothing's happening now because the static friction is building up. But eventually, what's going to happen? We're going to break the static frictional force. Now it rolled a little bit there because I'm not keeping this sensitive, right? I'm not going by the rules here, but it's hard to do. But I think you can see there that it's sliding without rotating. It can't rotate. There's no torque about the instantaneous axis of rotation. So this is really nice to use the instantaneous axis of rotation here to explain this. It's easy. Otherwise, you'd have to write down several equations, and there's several unknowns, and you'd lose a physical feel for what's going on. Okay, anybody have any questions about this? Okay, so now we're going to talk about angular momentum. This is analogous to linear momentum, or momentum of a particle, which we define to be the mass times the velocity. And this is going to be useful in the same way that linear momentum is useful to solve some problems. Usually we use linear momentum for collisions. Angular momentum, now that I think about it, angular momentum is not really used very often for collisions, even though the lab this week you'll be doing an angular collision. How can that be? Well, you'll see. Okay, we have a lab this week?
Yes.
Okay, good, thanks. But anyway, the angular momentum plays a big role for dynamics, okay? And in case I forget, I haven't told you something that I need to tell you, and I'm going to tell you now in case I forget. Nearly everyone, when they think about classical mechanics, and you ask them what's the most difficult subject in classical mechanics, it's rotational motion. Specifically rigid body motion in three dimensions. Like tops and gyroscopes, things like that. Most people consider it to be the most difficult thing. So we're headed into that territory, as you'll see. And tomorrow you'll see some remarkable demonstrations that, involve this. So anyway, we know that the linear momentum is of a particle is defined to be the mass times the velocity, and this turns out to be useful, mainly in collisions, as we saw. Now for rotational motion, the analog of the force is the torque, which is R cross F. So you might guess that the angular momentum would be defined as R cross P. You know, we got to tau, the torque, from the force by taking R cross that. We do the same thing for the angular momentum. We take R cross the linear momentum. So that is that's the definition of the angular momentum of a particle, okay? And from that we can get the angular momentum for an object. We just have to sum up all the individual angular momentums. Now I want you to notice something here, a special case. If this depends upon the origin, right? And here's an example. If my origin is here and the particle happens to be going straight out or coming straight in, what's the angular momentum? It's 0. These two vectors are parallel, it's going to be 0. Physically it's 0 because you don't see anything going around here. You know, you don't see something going this way or this way. They both are on equal footing here. You know, I look at this, I don't see this and I don't see that. Okay, so the angular momentum is 0 here. Okay, so a common case of angular momentum is uniform circular motion. Please note, there's no gravitational field here. This is, if you imagine this taking place on a smooth surface, you're looking down on it. Uniform circular motion, something that we've talked a lot about in this class, and we even did an experiment in it, right? So, we assume the particle here is small, has small spatial extent. It's acting like a particle rather than an extended body, because that's all we just want to exhibit right now, the angular momentum of a particle, something that doesn't have any important spatial extent. So it's going to be this radial distance here times, now because the momentum here is perpendicular to the radius vector here, the cross product, you know, the sine of the angle is 1. So we just multiply these two. It's similar to torque, which what we've been doing with torque. So the angular momentum here, this lowercase script L, is just going to be R times P, which is RMV. Where's the direction of the angular momentum? Okay, I got to take R cross, I take this cross that, I parallel transport this up here. So the angular momentum is out. And oh, by the way, how does it change in time here? How does the angular momentum change in time? Okay, how does its magnitude change? Oh, come on.
Magnitude shouldn't change.
Yeah, it's constant, right? Because this is uniform circular motion. So the magnitude, what about the direction of the angular momentum?
Yeah, it rotates into the circle.
Okay, so I've got this vector. Didn't we decide it's coming out here? R cross P. So as this moves around here, it's over here. What's R cross P? Neither the magnitude nor the direction change. Yeah. And that's going to be very important. Because I'll tell you right, the bottom line here is it takes torque to change the angular momentum. Angular momentum is like momentum, linear momentum. It doesn't want to change. You know, it's this inertia property. It tends to be constant. And in ideal situations it is. Only with a force can you change it. Only with a torque can we change the angular momentum. We will see that. Now there's a little bit of a problem here that I want to point out to you. And remember, this is the most complicated stuff in mechanics, right? This rotational motion. We naturally chose the origin to be at the center of the circle. What if we look for trouble here? And here's the situation, okay? And you'll notice L, you can see L is going to be constant in magnitude and direction here. Suppose we chose the origin, let's say down here. So that's what this diagram is supposed to convey here. Before we chose the origin here, now we're choosing it down here. Now, what's the angular momentum? Well, now I have the momentum, or the velocity, is into the board, right? So, I'm still going to get, where's my momentum going to be? The angular momentum. The velocity is into the board. I'm still going to get, there's a 90 degrees between this radius vector here and the momentum. But where does it point? Well, it points off here, perpendicular to there. And now what happens as it's undergoing uniform circular motion? It's going to rotate, it's going to trace out a cone here. The magnitude of the angular momentum stays constant, but its direction steadily changes. It's going to go around like this. When the particle's 90 degrees back there, it's going to be pointing out like this. It's going to go around. So that's trouble, okay? And we're going to have some explaining to do here. I just told you that it's a torque. There has to be a torque involved here. And it's hard to see that, but it's there. So we might talk about that later. I can't remember, but I don't want to talk about it now. But I just want to point out the difficulty here. Now, we can avoid this because usually what is important in when you have an axis that does not change direction, usually what's important is, oh, sorry, I failed to say something here. What's the magnitude here when we use this as our origin? Oh, sorry. Usually what's important when we have a fixed axis is the angular momentum, not the transverse direction here, but along the axis of rotation. So we would project this vector onto the axis. In fact, it's so important that people don't say what the angular momentum projected onto the axis. They say the angular momentum about the axis. But make no mistake about it. When people talk about the angular momentum about an axis, what they're technically saying is take the angular momentum vector and project it onto the axis. So when we do that here, you can see that what we're going to get when we project this involves a cosine theta. We plug in what L is, the magnitude, and you'll notice here that r times the cosine theta is just this moment arm distance here from the axis. So to get the angular momentum about the axis, which is the angular momentum projected onto the axis, I take the distance the particle is from the axis. That's what I've called this r perpendicular right here. Okay, this is going to be important for as we go on. So we've defined in general the instantaneous angular momentum of a particle. The total angular momentum of any system is going to be the sum of all the individual, you've got to sum over all particles, right? Vector sum. And that means, I should put an implication sign here, and that means that in the z direction, which we think of as the axis of rotation when it's fixed, at least, we're just going to be summing all the z components. So let's look at an example of that. Let's specialize to this case of a rigid body. All right, this is general so far. It doesn't have to be a rigid body. And and it's true for, the axis can be moving in any kind of direction. Let's go back to the previous chapter, in a sense, and just look at a fixed axis of rotation and a rigid body. What's the angular momentum? Now, in case I forget, and I didn't say it here, the actual full angular momentum could be pointing. Doesn't have to be vertical. Doesn't have to be pointing along the axis of rotation. Okay. It doesn't have to be. But for a fixed axis, it turns out that all that's relevant is just the angular momentum about the axis of rotation. So we would get it by summing over all the particles here. Each mass times its velocity, which in this case, at this moment, is going to be directly in, times this distance, this moment arm distance here. All right, so we have this sum. What's V equal? For a rigid body, V is equal to omega r. Remember that? The velocity is proportional to the distance from the axis. So I can substitute that. Why don't I have an I on the omega? I have I's everywhere else here. Why don't I have an I on the omega? Because all particles have the same angular velocity. That's associated with the entire body. So I can factor it out. And anyone, what's this quantity? It's a moment of inertia. So what we found here is Lz is equal to Iz omega. And for fixed axis, people usually don't want to drag this along. They just drop the z and write this. And now, this is one more rotational relationship that's easy to remember. And it's easy to remember because you remember for a system of for a particle, the linear momentum is the mass times the velocity, right? This is just the angular version of that. Instead of the linear momentum, you know, it's the angular momentum, and instead of the mass, we use the moment of inertia about the axis, and instead of the velocity, we use the angular velocity. So it's one more of these, add this to the list, this long list of correspondence between translational motion and rotational motion. And it also, we get the same, remember this is also analogous. It's also analogous for treating a system. The total momentum is the total mass times the velocity of the center mass. This is one of the things we established previously. And by the way, the direction of the angular momentum here, you can see all of these particles are all of these particles contribute up if it's spinning this way. So the angular momentum here is going to be directed that way. If it were spinning the other way, we would get the opposite. The angular momentum is pointing down. Okay, so we need the general analog of F equals ma. And here's what it is. From this expression of Newton's second law, we might guess that this would be, at least for a particle, sorry, we're going to deal with just a particle right now. So from here, thinking of this as a particle, we would expect to get this, just by replacing these quantities with their rotational analogs. And we can prove this in general. Look at this. Let's look at the rate of change of the angular momentum of a particle. Okay, well the mass is constant. The angular momentum is m r cross v. The mass is constant, it goes through the derivative. And now I got a different, this is a product. So you got to use the product rule. So the derivative of these two things, these are both functions of time in general. I differentiate them first and then take the product. Here it happens to be the cross product, it doesn't matter. Times the second factor, and then I take the first factor, the product, with the time derivative of the second. So that's just the product rule that you're all familiar with, except it's applied to a cross product here. What's this? dr dt is v, so what's any vector across with itself? 0. What's dv dt? That's the acceleration. So now, we bring the mass back through here and attach it to the A, and this is just going to be the net force by Newton's second law. And R cross F is the torque. So we just showed that this is true for a particle. It's true for a particle. Now, to apply this to a system, to an arbitrary system, we need to sum over all, we're going to sum over all particles. On the left-hand side, we're going to get the total net torque. Now there can be, when we have more than one particle, a particle can exert a torque on another particle. But the torques are going to be equal and opposite. So they cancel out. And what we're going to find here is that the net torque is necessarily the net external torque, okay? This net torque has to be the net external torque here. And on the right-hand side of the equation, we're going to get just the rate of change of the total angular momentum. This is a remarkable relationship. You will be amazed. And you're going to see, whoa, you're going to see something amazing right now, in a minute, okay? But you'll see a lot more tomorrow. This happens to be very general. Incidentally, you might guess that The net torque is the moment of inertia times d alpha dt. That only works when the axis is moves, if the axis is either stationary or moves parallel to itself. When you have a top or a gyroscope, something like that, this does not hold. This holds. That does not. So as I mentioned, we're going to see some amazing, we will see some remarkable things here. And I want to show you something right now. How many people have heard of countersteering? Any motorcycle riders here? Wow, yeah. My father got into motorcycles once. This is this retired from NASA guy that I told you about before, right? Remember the golf clubs? So he got it, I don't know, he was in his 50s or he got into motorcycles. And they actually, he took a class because motorcycles are dangerous. In fact, everybody I've known who's ridden a motorcycle has been in at least one accident, okay? So, you're in a motorcycle here, and you're taught this in the class. He was taught this. And so you're moving along, okay? This is one of your wheels, this is the front wheel. And all of a sudden you see something you have to avoid. In a car you don't really care, you know, but on a motorcycle it could hurt you, right? Like a pothole or something like that. Suppose you decide that you need to, very quickly, that you need to go, let's say that the pothole is a little bit on this side, so you want to go that way. What do? Anybody who knows about countersteering? Some of you raised your hands. You push the opposite way you want to go by pushing this way. See what I did there? By pushing this way, the wheel rotates this way, and then countersteering is actually complicated. There's been a lot written about it. You can look it up on the internet. But this is the first step. By pushing this way, all of a sudden the wheel goes this way. It banks this way, which helps you go this way. Okay? Now there's a little more to it than that. It gets complicated, and you can look it up. But that's the idea, and it really works, okay? This time I pushed here, right, if I want to go that way. This works with bicycles, although it's not dramatic, and it's usually not necessary because you don't move that fast on a bicycle. But people who do probably know this, okay? So the last thing we need to do here is, why is this inclining like this? Well, it all comes from this equation. Where's the angular momentum? Put your fingers in the direction, it's this way. Where's the torque? I'm exerting a force this way, R is this way, the torque is this way, the angular momentum is this way. Which way does the angular momentum change? It goes this way, and that's exactly what it does. This is not obvious. This is not obvious. But it's useful to know because it could save you from having an accident, right? Okay, thank you.